My name is Michaela Brchnelová. I'm from the capital of Slovakia, Bratislava, and I'm here to present you my work on Tycho supernova remnant accelerating cosmic rays up to PeV electron volts. Firstly, I'd like to remind you of that I'm still just a high school student, hence my presentation will probably be much more or less professional as yours were. And I'm not going to attack you with dozens of formula and very difficult physics because I'm just a high school student. And I know that there's still much left to be improved, hence I'll appreciate and I'll be grateful for any feedback you can provide me with in the end of my speech. So firstly, I'll talk about some basic introduction, where in a bit I'm going to explain the basic terms like magnetic field amplification and diffusive shock acceleration. Then we will move to the first part of my research that were the theoretical presumptions on the rate of magnetic field amplification. And in the end, I'll talk about my observations in comparison of observed and presumed values. It is a matter of fact that the energies of cosmic rays that we detect on Earth are in fact very, very high, some of which we are unable to explain. At least we were unable to explain them recently. Specifically, I'm talking about the energies that we also address as the Ni energies, as you can see on the graph. They are from 10 to the power of 15 electron volts to 10 to the power of 17 electron volts, and the whole origin is believed to be supernova remnants, thanks to a beautiful process known as a diffusive shock acceleration. And it should work like this. Let's imagine that we have got a typical forward shock region, the forward shock of supernova remnant, and it is a very inhomogeneous region. Hence, it surprisingly contains many inhomogeneities that are both upstream, that is the region behind the contact discontinuity, and downstream, that is the region after contact discontinuity. And the difference of densities of these plasmas upstream and downstream is responsible for that the total amount of these inhomogeneities upstream is significantly higher. And now let's imagine that some cosmic ray enters the shocks from its front. It is being scattered off these inhomogeneities back and forth through the shock, and it gains energy after every head-on scattering or head-on reflection. And because the total amount of these inhomogeneities upstream is higher, on average, the cosmic ray leaves accelerated. However, even with a process like this, it was found after a few simulations that we are only able to reach merely some electron volts. So it is really a low value. Nevertheless, astrophysicists Bell and Lucek continued with the simulations and found that they came up with a theory of magnetic field amplification, according to which the cosmic rays that are confined in this shock tend to create waves because of their charge, and these waves result in a magnetic instability. And because of the interaction with other magnetic instabilities and other cosmic rays, this magnetic instability is growing and growing, so that its magnitude eventually exceeds the former magnitude of the magnetic field. And that is what we call a magnetic field amplification in supernova remnants. So theoretically, in case a magnetic field of supernova remnant is much, much higher than those default 3 to 5 microgrosses, we are able to reach those Ni energies, theoretically. And this is the biggest problem because, in fact, the measuring of magnetic field of supernova remnants is quite a messy business. Some attempts were made to measure this magnitude of magnetic field through fitting of radio and X-ray spectra with the Cyclotron model, but this method suffers from many inaccuracies and systematic or procedural errors. Therefore, an astrophysicist, Simon Reynolds, came up with another idea, another way to measure this magnetic field through the measurements of the thickness of cyclotron halo. And this cyclotron halo is consisted, when we have a forward shock, it contains the orbiting particles that are diffused ahead of the shock and are orbiting the magnetic field lines that are usually oriented parallelly to the shock's normal. So this is the shock, these are the orbiting cosmic rays, and because there are electrons that emit cyclotron radiation, we are able to observe such a cyclotron halo in front of the forward shock. Hence, the thickness of this cyclotron halo depends highly on the cosmic ray energy and the magnitude of the magnetic field that we are trying to measure. What we must realize too is that what we really see is the cyclotron emission of these cosmic rays, and hence these electrons are suffering from huge cyclotron losses. And therefore, even though the protons are accelerated in the same manner as the electrons, the total energy of the protons will be even higher. So this was our main aim, to observe such a cyclotron halo around Tycho supernova remnant, to measure its thickness, and hence to determine or to estimate the value of magnetic field there, and hence to either to support or to disprove the theory Bell and Lucek have suggested. So, one attempt like this has already been made by Stephen Reynolds. He tried to observe and measure such a halo around SN 1006. However, he was even unable to observe this halo around SN 1006. So firstly, we need to make some presumption on the halo thickness, because there is generally no point in searching for something we are even theoretically unable to resolve. And we wanted to prove that the magnetic field amplification theory is correct. Hence, all the calculations were made based on the equations derived from the Bell and Lucek physical models and their simulations. We can see that if we were calculating with a non-amplified model with a magnetic field of 3 microgausses, we are only able to reach maximum energies of 15 teraelectron volts, which is quite a deplorable value. When we wanted to find the achievable rate of magnetic field amplification in Tycho supernova remnant, we found that we needed to know the electron density, and not just some ordinary electron density. We needed to know the electron density precisely in the region of our interest that you'll see later. So we have extracted a spectrum of our region, fitted it with this spectral model so that we achieve chi-squared better than 1.5, and the obtained electron density was 0.7 per centimeter cubic. And calculating with this value of electron density, we found that we are theoretically able to achieve energies of 140 teraelectron volts in Tycho supernova remnant with the magnetic field 85 microgausses. These are both values upstream, and because of a compression of the shock downstream, we are even able to reach magnetic field 280 microgausses, what corresponds to the maximum cosmic ray energy of almost half a peta-electron volt. So we see that, yes, theoretically it is possible to reach almost peta-electron volts in supernova remnants, but this is still theoretically. And according to these energies and magnetic field, the resulting thickness of this cyclotron halo that consists of orbiting particles shall be around 0.35 parsecs. That is in fact the Lamb radius of the orbiting particles multiplied by the factor of their velocity divided by the velocity of the forward shock, because they are diffused. So we are searching for something that wide, and this shall be definitely observable. For our observations, we have chosen Chandra, and both Chandra SSS array and X-Newton epigmos arrays, because of Chandra's better spectral resolution and because of X-Newton's better spectral efficiency. And we have chosen to study the western rim of the supernova remnant because, as I have shown in my previous work, both northern and eastern rims of Tycho are expanding into very dense cloud interstellar medium, and the southern rim was not very well observable for Chandra, so that's why we have chosen the western rim. And this is the picture of Tycho in the energies above 3 kiloelectron volts, what is a pure non-thermal emission for Tycho. And we can see that there's really some weird region in the very edge of the forward shock where the total flux above these 3 kiloelectron volts was beginning to rise really rapidly. But just because it is weird, we cannot say that this is the cyclotron halo. No, that's why we have made spectral comparison. Firstly, we have extracted a spectra of the average forward shock region. This is what the forward shock, so it was somewhere here. And we can see that, yes, there is still some cyclotron non-thermal emission about those 2.53 kilotron volts, but mostly there is very, very hot gas that is emitting at 1 kilotron volt and 2 kilotron volts. And when we extracted a spectrum of our suspicious halo region, we can see that, yes, there is still some gas, but on the other hand, the spectrum is much more continuous, and there is a considerably large ratio of the pure non-thermal cyclotron emission, what means that there is a very big amount of high energetic particles that emit this cyclotron radiation, which is the proof we needed to have in order to conclude or to presume that this is really the cyclotron halo we are searching for. So, we have then made more detailed analysis. We have made contours that were defining the areas where the total count rate above 3 kilotron volts was beginning to rise that rapidly, bordered it with regions, and the average thickness of these regions of the cyclotron halo was 0.002 degrees. So now we have got two beautiful values, 0.35 parsecs and 0.002 degrees. But another problem emerged because, in fact, the distance of Tycho supernova is unknown. There is just some range of distances that is probable. Estimations had been made by other astronomers, and it claims that the distance of Tycho should be in range from about 2 kiloparsecs to 3.5 or 4 kiloparsecs. So we asked ourselves, how far would Tycho SNR be in case that what we see as 0.002 degrees is in fact, in reality, 0.35 parsecs wide. And the resulting distance was 2.8 kiloparsecs, what is an outstanding agreement with the estimations made by the other astronomers. So based on this, we can say that yes, probably what we see as the cyclotron halo in Tycho is really those 0.3 to 0.4 parsecs wide. So in summary, we have measured the electron density in the region of the forward shock. Then we have estimated the rate of magnetic field amplification for Tycho, and accordingly the resulting thickness of the cyclotron halo. And then we have observed this cyclotron halo in the western rim of Tycho supernova remnant, measured it, proved its non-thermal cyclotron nature, and showed that it is really as wide as we could presume. And because of that, we have shown that what we really see is 0.3 to 0.4 parsecs wide, and that we really need 85 or from 80 to 90 microgauges in order to form such a halo. We have shown that our results support the theory of magnetic field amplification because such a halo would not be possible with those default 3 microgauges. I must also admit that our results, those 18 microgauges upstream, correlates very well with the method of spectral fitting of radio and X-ray spectra. However, their inaccuracies are quite larger. So, I'd like to thank my consultant Matúš Kocka and also Michal Záček for their feedbacks and reviews. Also the offices of X1 Newton and Chandra for that they were willing to allow me to use their data, and also the Synergy team for that I can be here now. Thank you for your attention. As I said in the beginning, I'll appreciate really any advice, any critiques, anything you can provide me with. I hope I will be able to answer your questions, and thank you for your attention.